Okay, good morning, everyone. Today we'll cover mesh current analysis. When I say cover, we will actually introduce the topic. I will go over a little bit of the theory, but we won't have time to cover the example problem. And so I will postpone homework 10, mesh current analysis, which is due tomorrow. So we'll cover the theory today, and then on Wednesday, we'll finish the theory, cover the example problem, and then I will make the homework due either Wednesday night or Thursday night. More likely Thursday night. Okay, there's 3 problems in there, but similar to node voltage analysis, mesh current analysis, again, it's 3 problems, shouldn't take long. And I will post some hints so that students can actually refer to those. Okay, so let's take it from the top. Mesh current analysis is an analysis technique similar to node voltage analysis. It allows us to find or determine the unknown voltages and currents that appear in a circuit. In the case of node voltage analysis, we applied KCL to generate our equations. In mesh current analysis, we would apply, KVL to generate our equations. Okay. Both techniques are very similar. But again, as I said, the purpose is to generate enough equations to solve for the unknown variables. In NVA, node voltage analysis, the unknown variables are the node voltages. In mesh current analysis, the unknown variables are the mesh currents. So let's look at what a mesh is first, and then we'll talk about the mesh current analysis technique. So a mesh is basically a simple electrical loop. Is everyone familiar with the concept of an electrical loop? Hopefully. So a loop is a closed pathway. Actually, let me elaborate on this simple. So the simple loop simply means it does not contain any other loop inside it. Okay, it does not contain any other loop inside it. Now a loop is a closed electrical pathway. Simply put, if you take any point in a circuit and you go around the electrical branches, or you go around the branches of the circuit and you come back to that same point without going back on itself, then that is a closed pathway. So for instance, if I label the bottom left node as A, how many pathways can we take to come back to A? The most obvious one is the outer loop. Let's call that as loop 1, right? You go around the outer loop. You go through VA, R1, and come back to A. Make sense? Right? That's an electrical loop. It's a closed pathway. You can go around that pathway and you come back to the same point. That is an electrical loop. But you could also take this pathway. You don't have to draw out any of these. These are just for concepts and understanding. Let's call this 2. It also is an electrical pathway. Right? There are more loops in here. This is one more loop, as well as this. And call this 3, call this 4, kind of messy. What do we notice? 2, 3, and 4 are nested inside 1. So loop number 1 contains 2, 3, and 4. Loop number 3 contains loop number 4. Loop number 2 also contains loop number 4. However, loop number 4 does not contain any other loops inside it. And hence, loop number 4 is a mesh. So a mesh is a simple electrical loop that does not contain any other loops inside it. It's a simple loop. Identifying meshes is rather straightforward compared to identifying nodes. Okay. So let's take a 10-second pause. Let me know if you have any questions. There are actually more than 4 loops here. I have not even covered the right side of the circuit. If we cover the right side of the circuit, we can find further 2, 3 more loops. But for now, explanation purposes, here we have 4 loops. And out of those 4 loops, only one of them is a simple loop. So a simple loop is a mesh. A mesh can be classified as a subset of electrical loop. Any questions? Okay. All right. So I'm going to wipe these out because I need to use the circuit diagram for something else. Okay. So we would identify this as mesh 1, mesh 2, and mesh 3. 1, 2, and 3. Again, simple electrical loop, a closed pathway that does not have any other pathway inside it. So identifying meshes is easier. It's visually easier for our brains. Okay. Whereas with a node, we actually have to look at it and make sure that connections are not connected with a wire or a component. Does everyone see what I'm saying? Right. So mesh is easier to identify. So first thing in mesh current analysis is we take a look at the circuit diagram, identify all the meshes, and we assign mesh currents. Meshes and assign currents to it. Assign mesh currents. Okay, assign mesh currents to each mesh. Now, mesh currents are not real. They are purely theoretical or hypothetical, if you will. Theoretical or hypothetical. Okay, they are not real. They do not exist in real life. Okay, they do not exist in real life. In your own engineering fields, when you try to solve engineering problems, you would have come across solutions where you make certain assumptions. Assumptions are what allows us as engineers to solve a given engineering problem. And so is the same case with electrical engineering. We make certain assumptions. Sometimes they are approximations. Sometimes they do not even exist in real life. Okay, and this is one of those cases. And I'll explain how and why that would work. Mesh currents, first of all, we say that they're flowing to only that single mesh. Okay, so M1 has I1, M2 has I3, M2 has I2, and M3 has I3, right? M1, M2, M3, I1, I2, I3. And they each have a direction. They're either flowing clockwise, which all 3 of these are, or you could assume counterclockwise. It does not make a difference. Similar to node voltage analysis, it does not make a difference which node you choose as your reference. So is the case here. You can choose either clockwise or counterclockwise for your mesh currents. And you can mix and match. There would be some cases where you would want one mesh current to be clockwise, another one to be counterclockwise. It does not make a difference. Okay, so direction can be clockwise or counterclockwise. It will not make any difference to your analysis. When you add up the voltages, you have to take those directions into account. Okay. So let's look at a shared component. When I say a shared component, means there would be a branch that is shared between two meshes. So if we take a look at the circuit diagram, we see that R2, VB, the voltage source, and the resistor R3 are shared between two meshes. If we simply take, let's say, R3, for instance, R3 has a current coming from mesh 1 as well as a current coming from mesh 2. So I1 and I2. So is the case with R2. R2 is shared between I1 and I3, or mesh 1 and mesh 3. And because of our chosen direction, when we choose all currents to be clockwise or the same direction, it will always, always, always happen that a shared branch, the currents will be going in the opposite direction. They will never, ever be in the same direction. You can try that out for yourself. Apply these concepts to any circuit. If you take all the meshes and you choose all mesh currents to be clockwise or counterclockwise, then the shared branch will always have currents flowing in the opposite direction. Okay, it'll always happen. So R2 will always have I1 and I3 going in the opposite direction. R3 will always have I1 and I2 going in the opposite direction. That means you have one current going up, one current going down, or left and right, which is physically impossible. Current through a resistor would only flow if both the points are at two different levels. If both ends of the resistor are exactly the same electric potential, then the voltage across those 2 points is equal to 0 volts. One end of the resistor has to be higher for current to flow. Current always goes from high to low, right? So if we are saying that the current is flowing from one end, from my right hand to my left hand, then I'm saying the right hand, the point is at a higher level. At the same time, I cannot say that this point is at a higher level, right? Physically impossible. Hence, mesh currents are hypothetical. They are not real. They do not exist in real life. Okay? You cannot have a single point higher and lower than the other at the exact same time. Now, semiconductor device physics, that's a little different. We have electrons and holes both contributing to a current. So there, at those times, that's a completely different case. But I don't think anyone here is studying semiconductor device physics, not unless they take electronics, okay? For the purposes of our analysis, electrical engineering, electric circuit analysis, we stick with this. We cannot have two currents flowing in the exact same component in the exact opposite directions. All right, questions? Any questions? So far, so good? Yes. Yes. The question being asked is, can we apply measurement analysis to voltage and current sources? The answer is yes. Similar to node voltage analysis, doesn't matter how many voltage sources or how many current sources we have in the circuit, it's the same thing. You can apply mesh current to any circuit. Any other? Okay, then let's take a look at mesh 1. And we'll apply KVL and then generate our equations. So we apply KVL in mesh 1. And we see, let me draw this out right here. So mesh 1 has I1, R2, R3, and VA. Now again, we are applying KVL. So if you have a preferred method, you stick with that method. You do not have to do what I do. Okay, typically what I do is I start at the bottom left corner and I sum up the voltages. So I would have VA, VR2, and VR3 all summing up to 0. I'm going to take VA as minus, VR2 as plus, VR3 as plus. Typically what students would have learned would be a voltage source minus the resistor voltages equals to 0. So VA minus VR2 minus VR3 equals 0, which is the exact same equation. No difference. So you apply KVL with the method that you are comfortable with. Okay. Then we use Ohm's law and express all resistor voltages in terms of the mesh current. V equals IR. R in this case is R2 and R3, and I is I1. So what can we write about VR2? Absolutely. And then VR3. Do we all agree, or are we thinking about it? The answer is correct, but we have to extend to include the other mesh currents also. And so yes, VR2 would be I1 times R2, but we have to extend that to account for I3 and to account for I2. Again, hypothetical currents, but we still have to account for those in our analysis. So VA, of course, is the voltage source, so that would be known to us. VR2 would be I1 minus I2, oh, sorry, I3. R2. And then VR3 similarly would be I1 minus I2 times R3 equals to 0. So again, standard Ohm's law, application of Ohm's law would give us I1 times R2 and I1 times R3. But because R2 and R3 are in a shared branch, we have to account for the other mesh currents that are flowing through there. For R3, it is I2. And for R2, it is I3. And if you notice, both currents are in the opposite direction. Both currents are in the opposite direction of I1. And hence, it'll be I1 minus I2 and I1 minus I3. Let's take a 10-second pause, think over that, and let me know if you have any questions. Yes. That is absolutely correct. So the question being asked is, are we subtracting I3 and I2 because we are looking from, we are adding up the voltages for M1, mesh 1? And the answer is yes. Because it is mesh 1, the other currents which are flowing in the opposite direction would be subtracted. But the extension of that answer would be, if we chose I2 and I3 to flow in the opposite direction, meaning counterclockwise, then they would be flowing in the exact same direction as I1 also, through the branch. Okay, let's say I1 was clockwise, which is what we have here. But if I2 and I3 were both counterclockwise, if they were both counterclockwise, then I2 and I3 would be flowing in the same direction as I1 for R2 and for R3. Then it would be I1 plus I2 and I1 plus I3. When you get to mesh 2 and you get to mesh 3, both the currents will be negative. So it balances out. Let's stick with this for now. Okay, if we stick with this for now, all three currents are counterclockwise. So from the perspective of each mesh, it would become the mesh current would be positive, the other currents would be negative. Yes. Yes. The answer is yes. So question being asked is if I1 was counterclockwise, would that become negative? The answer is yes. And again, it's also the way you add up KVL. Okay, the way you add up KVL also accounts for the plus and then minus sign. So it gets a little complicated if you take it that way. But the logical conclusion or the end result from all of these assumptions, whether you choose clockwise or counterclockwise for your mesh currents, or whether you add up the KVL voltages in a clockwise or a counterclockwise manner, the end result will always be the same. Okay, it does not matter which direction you choose for your mesh currents. It also does not matter how you apply your KVL, because we would stick with the same assumptions when we get to mesh 2 and we get to mesh 3. And that's why those equations will balance out. So here, instead of having I1 minus I3, if I had a double positive, if I had I1 plus I3, and here I had I1 plus I2, when we get to mesh 2 and mesh 3, they would become double negatives. And then they would balance out. Yes. So the question being asked is, every circuit that we analyze with mesh current analysis, can we just choose clockwise for all currents? And the answer is yes. We can choose all currents to be clockwise at all times. The only time I would recommend choosing a different direction would be if there's a current source in there. If there's a current source in there, especially if that current source is not shared with any branch, then it makes sense to choose the mesh current going in the same direction as the current source, because we'll automatically have an answer for that mesh current. And we'll look at an example that does exactly the same. All right, other questions? Let's look at mesh 2. So if you look at mesh 2, and I apply KVL, sounds like they're having a party outside. M2. So we have R3, R4, and voltage source VB. Okay. So voltage source VB R3, R4, and you have mesh current I2, but you also have mesh current I1 coming down. So now if I apply KVL in this loop, I would have VB plus VR4 plus VR3 equals to 0. And once I apply Ohm's law, I can write VR4 is I2 times R4 plus, now this time it would be I2 minus I1. Equal to 0. Take a pause while you write it down, think over that, and let me know if you have any questions. I would point out in mesh 1 that I1 is entering R2 from the left. Point of entry is always positive. So R2 left side would be positive, right side would be negative. Again, I'm referring to M1, mesh 1. And then I1 enters R3 from the top. So the top end of R3 is positive. Point of exit down below is negative. But when we account for the other currents, then the point of entry changes. The point of entry is now positive, which is the bottom, and hence it's minus. So think over that and let me know We are out of time. If you have any questions, I will be in my office later today from 1 to 2:30 for students. And then we'll pick up here again on Wednesday. Okay.